All right.
When we correct something, we have to give it to you and I hide it.
Okay. I think it's already good. So yeah, it's in the grade book. All right, ladies and gentlemen, if we could come to order, that'd be really cool. Got a lot to talk about. So we left off last time talking about covalent bonding, and we remind ourselves that covalent bonding happens when two atoms agree to share an electron. So fluorine says, hey fluorine, you have 7 electrons. I have 7 electrons. If you share one and I share one, then you'll have 8 and I'll have 8 sometimes. And they remind themselves that since the electrons are being shared back and forth so fast, it looks like they both have an octet. Now, a single bond occurs when each atom donates 1 electron to the pair. So a single bond is the weakest bond, but it's also the longest bond. Now, if 2 atoms each share 2 electrons, then there are a total of 4 electrons in the bond, 2 from each atom, and that's a double bond. And a double bond is stronger than a single bond, and it's also shorter. And then if one of the atoms donates 3 to the other, and that other donates 3 back, you get a triple bond where there's actually 6 electrons moving between the atoms. A triple bond is the strongest bond there is, as far as we know. It's also the shortest bond. As far as we know, there are no quadruple bonds that we've noticed. So there are doubles and triples and singles. And when atoms covalently bond, the electrons are zooming around between the atoms, and the protons of atom A are attracted to the electrons of atom B. And the protons of atom B are attracted to the electrons of atom A. And they want to get as close as possible. But they don't want to overlap too much. Why? They would be unstable. Why would they be unstable if the clouds got too close? Their electron clouds got too close. What do electrons and electrons do? They repel. Exactly, they repel. So you want to balance out the attraction of the nuclei for the electrons of the other atom with the electrons and the electrons of the other atom's repulsion. So you balance that out. And when you've balanced it out, you're going to get to a low potential energy, a low potential state. Now in chemistry, low potential is the way to go. Low energy is the way to go. Low energy or low potential is stable. Just like you would much rather spend the day in your lazy chair watching cartoons or binge watching Netflix than you'd rather be at school running around and having to do things. They're like, I'm a lot less stable balancing on one leg than I would be hanging out in a lazy boy. So low energy is stable. Stable molecules attain a low energy area, and that's low energy. Okay, does this stuff make sense?
Yes.
A little bit? Okay, cool. Can we move on? Let's move on. Okay. Okay. So, now we talked about electronegativity in the past. This is a diagram that's in every textbook. And it basically ranks bonds according to how much of them are ionic or covalent. We're not going to do that. We're going to rank all of our bonds as either being all ionic or covalent. And there's 2 types of covalent bonds. Now remember, an ionic bond happens when 2 things stick together. What 2 things? What 2 things stick together to form an ionic bond? Negative and positive, metal and non-metal? Yeah. So again, we remind ourselves, if we look at the giant periodic table on the wall, follow the little green dot, we got metals over here on the left, and we got non-metals on the right. And anytime a non-metal and a metal bond together, it's going to be an ionic bond, like in the video. Sodium was +1, chlorine was -1, because sodium gave up its electron to chlorine, and the negatively charged chlorine sticks to the positively charged sodium, stick together. So when you have a metal and a non-metal, when you have a cation and an anion, when you have a positive charge and a negative charge, you get a covalent bond. I'm sorry, you get an ionic bond. You get an ionic bond. A covalent bond occurs when they share, but they might not share equally. They might not share equally. For instance, when carbon and oxygen share an electron pair, they don't share equally. So if I got an oxygen atom and I got a carbon atom and they make a bond, they don't share that bond equally because oxygen has more electronegativity than does carbon. We remind ourselves that what is the most electronegative atom in the periodic table? Fluorine, exactly. So fluorine is the most electronegative, and it decreases as we go down this way to cesium and francium, which have the lowest electronegativity. We increases this direction up to oxygen, fluorine, and chlorine that have the highest electronegativity. So oxygen has a higher electronegativity than carbon. If you were to draw the electron density of that electron pair, it probably looks something like this. Okay? Where most of the electrons are spending most of their time around oxygen, because oxygen's more electronegative. So if that happens, then we have a side of the bond that is negativeness. Which is the side of the bond has the most negativeness? The oxygen side. So the oxygen side has the most negativeness, and if that side's negative, this side must be positive. And what little symbol do we do to show negativeness or positiveness? Yeah, the partial charge. It's like an S. So it's like an S with a little loop on it. So we have a partial negative and a partial positive. And then we have another thing that shows kind of like a shortcut. What's the shortcut we use to show partial positive and partial negative? We wrote the S thing, but what else?
The dipole.
Yeah, the arrow, exactly, the dipole. Exactly, the arrow, the dipole. And dipoles start at the positive and go to the negative. So the dipole points from the partial positive to the partial negative, and the oxygen's partially negative because oxygen is more electronegative. Does that idea make sense? Give me a thumbs up if that idea makes sense to you. Looks like about half. Okay, let's go over it from the top. If carbon bonds with oxygen, carbon gives an electron to the bond, oxygen gives an electron to the bond. But because oxygen is way more electronegative than carbon, oxygen says, hey, bonding electron, you're spending most of your time around me because I'm most electronegative. And there's nothing carbon can do about it. So if you were to draw the density of that bond, then the electron's going to spend more time around oxygen, making the oxygen negative-like, making the carbon side positive-like. And we show that with a dipole, which starts at the positive and points to the negative. Okay? Give me a thumbs up if that makes sense to you now. Better. Okay. So sometimes when they bond, they're actually identical. Okay? Now, when they're not identical, when they are different, we call this polar. This is a polar bond. It's a polar bond. Just like a magnet has a north pole and a south pole, just like the Earth has a north pole and a south pole, bonds have a positive pole and a negative pole. So it's a polar bond. Now sometimes they might be identical. For instance, if oxygen bonds with oxygen, the bond they make is the same because oxygen has the same electronegativity as oxygen. So if you were to draw the electron density, pretend that's the same. There you go. So if you were to draw the electron density around the oxygen, then it would be the same around both oxygens. If this bond is called polar, what do you want to call this bond? Nonpolar. Nonpolar. Let's call it nonpolar. Sounds good? We'll call it nonpolar. So in a nonpolar bond, the electrons are shared evenly, like in O2. Although it's kind of, just go ahead and be accurate. In O2, we'll find out later on that this is actually a double bond. We're going to learn about how that is and why that comes about today. Okay? So we're going to classify all the bonds as one of three types. It's either going to be ionic, because it's a metal and a nonmetal, or cation and anion, positive, negative. We're either going to call it ionic, or we're going to call it nonpolar covalent if there's two nonmetals are the same, or polar covalent if the two nonmetals are different. Now realize there's this crazy spectrum here where it's like, they're within 5%, you can call it we're not going to play that game. We're not going to look at gradients. We're just going to say it's ionic if it's a metal nonmetal. It's polar covalent if it's two nonmetals that are not the same, and it's a nonpolar covalent if there's two nonmetals that are the same. We're just going to say boom, boom, boom. Not going to worry about the gradients or the angle or the percentages. Okay, how are we doing? Give me a thumbs up if we're ready to go. Moving right along. Okay. So we're going to spend some time talking about intermolecular forces. What does intermolecular mean? It has something to do with molecules. Inter means what? In between. Excellent. Yeah. So international business is business between nations. Intermolecular means between molecules. And particularly intermolecular forces is the attraction between molecules. Like I have two magnets here. And the magnets want to stick together. Even though they're not sticking together, there's still an intermolecular intermagnet attraction for this magnet and for this one. This magnet has a north and a south pole. This magnet has a north and a south pole. And they repel when they're lined up, and they attract when they're not. So it's like, no, 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 you're north-north. Ooh, north-south, I love it. And they stick together. Okay, molecules do the same thing. If you take a molecule that has a positive end and a negative end, it's going to try to line itself up towards a positive and negative end of another molecule. That's an intermolecular force. The positive of one molecule wants to arrange itself with the negative of another molecule. And this is actually a review, but if you like to write stuff, there you go. We're going to work with water and ammonia a lot, because water and ammonia have polar bonds. And they end up being, the bond dipoles come together to form a molecular dipole. So you sum up all the bond dipoles, and the sum of all those bond dipoles becomes a molecular dipole. It's like imagine 4 people playing tug of war. You sum up the 4 people all pulling in one direction, from the 4 people pulling the other direction, and whatever the difference is, that's the actual win, that's the tug of war. Same thing here. This bond dipole and this bond dipole add up to be a molecular dipole. This bond dipole and this bond dipole and this bond dipole add up to be a molecular dipole. And we're going to practice this a lot. Okay, so dipole forces are the intermolecular attractions between molecules that have dipoles. The positive of one on the negative of another. The positive of one molecule attracted to the negative end of another molecule. And it should make sense that the more polar a molecule is, the stronger dipole-dipole force would exist in those molecules. Well, what is this useful for? Well, the stronger the molecular dipole's attraction for other molecules is, the tighter they want to be together. The molecules want to be together. So it plays a role in the states of matter that the material can be. Think about it. If you had 2 molecules, or 2 types of molecules, that have very, very high, very strong intermolecular forces, do you think they'd rather be a solid stuck together or a gas flying all around? If molecules are stuck together very strongly, what state of matter do you think they should be?
Solid.
They'd want to be a solid. Okay? And that's how you determine whether something is a solid, a liquid, or a gas. You look at how strongly they want to stick together versus the movement around them. Hydrogen bonding is really slick. Hydrogen bonding is a special type of intermolecular force that occurs between the hydrogen end of one atom or one molecule and a partial negative end of a different molecule. It's frequently encountered in water, because water is so polar and it has two hydrogen ends. So once again, a water molecule looks like that. And if you were to draw it, it looks something like this. And there's a partial positive here and a partial negative there, giving it a pretty good sized dipole. Well, the partial end, the partial positive end on hydrogen is strongly attracted to the partial negative end on other hydrogens. This is why water, among other things, is sticky. And the weird thing about water floats. You might have noticed this, that water floats in its liquid when it's a solid. Solid water floats in its liquid, which is odd, and you'd expect that a solid, where the molecules are closer together, would have a higher density or a lower density than its liquid? Higher. And that's the case for almost everything. Almost everything, when they solidify into a solid, is more dense than its liquid. But not water. Water is actually less dense than its liquid. Its liquid actually its solid actually floats in its liquid. Unless you're the producer or director of G.I. Joe. At the end of G.I. Joe, Cobra's base is under a glacier. They hide it under a glacier underwater. And how does G.I. Joe destroy Cobra's base? They blow up the glacier, and the glacier falls onto the base. Because everybody knows that large pieces of ice float while small pieces of ice sink. I'd tell you to watch the movie, but don't. It's a terrible movie. That's just like, I watched that and I'm like, has nobody in Hollywood ever had a drink? Ice floats, no matter what size it is. Just because it's a glacier doesn't mean it's going to sink when it's broken up into little pieces. Oh, by the way, there was also back in the 30s, when we started to build military bases around the world, there was a senator who was concerned that if we built a military base in Oahu, in Hawaii, that Hawaii's, the ocean level, the water level, that he was concerned that if we built a base in Hawaii, that the water level in Hawaii would actually rise. Because there would be a lot more people in Hawaii. Look it up, it's true. You guys realize that the islands don't float, right? Okay, good. They're stuck to the ground. Okay, so what's really cool about water is this whole time you've been making snowflakes, you've been making them wrong. Because snowflakes are not 8-sided. Like your kindergarten teacher told you to fold it and then fold it again and then cut. So you had an 8-sided snowflake. Yeah, that's wrong. So next time you see an 8-sided snowflake, point out to the 6-year-old that she's doing it wrong. Because all snowflakes are 6-sided. All snowflakes pick up a hexagonal shape. Because when water molecules freeze in position, the partial positive of this hydrogen is attracted to the partial negative of that water, oxygen part of the water. And the partial positive here is attracted to that negative. And the partial positive here is attracted to that negative. And the partial positive here is attracted to that partial negative. And the partial positive here is attracted to that partial negative. And what you get is a hexagon. Yay. So all snowflakes are 6-sided, at their core are 6-sided shapes. It's pretty slick. But why does that make ice less dense than liquid water? Well, look around. Look how many people are fit in this room. There's about 33 of you. And you're taking up a lot of space. What type of matter are you emulating right now? You're solid. You're emulating a solid because you're fixed in position. But when the bell rings, you'll all get up and you'll squish together in an irregular form and you'll emulate what? A liquid. And you'll take up a lot less space because right now you are fixed in position. There's a fixed amount of space between all of you. And that's what happens here. There's a fixed amount of space between all of the water molecules causing them to spread out and form these crazy hexagons. And that makes solid ice less dense than liquid water. Isn't that neat? I think it's neat. If you don't think it's neat, you're just wrong. Okay, so next question. What is in the gap? What's in the gap? Who said nothing? Exactly right. Nothing. Okay, it's not air, because air is oxygen and nitrogen molecules. It's not air, it's nothing. What weighs more than nothing? Everything. So nothing weighs less than nothing, so everything weighs more than nothing. So if you put nothing in between the molecule will have less density. Does that make sense? Yes. Excellent. Okay. Oh, also this is kind of fun. You guys heard of Watson and Crick, right? Just little trivia. Yeah. So what did Watson and Crick do? Something about the cell. They predicted the shape of DNA. So Watson and Crick predicted the shape of DNA, and they didn't see DNA. You can't look at DNA under a microscope. It's like, that's its shape. It's a molecule. It's a big molecule, but it's still simply too small. What they realized is that one side of the DNA molecule was attracted to the other side of the DNA molecule. Well, if this hand is attracted to this hand, how does this hand go touch this hand? Yeah, you bend your body until they come together. And that's what they said, okay, so if this side of the big H is attracted to this side of the big H, then the H would simply bend, and that's what happens. The H's bend, and we get our twisted ladder, our double helix. Okay, there's another intermolecular force that has a lot of names depending upon what side you were rooting for in World War II. They might be called London forces, or London dispersion forces, or von der Waals forces. Again, depending on what side of World War II you were rooting for. London forces, von der Waals, or dispersion forces. And these are forces that exist in every type of molecule, even if it's not polar. Polar and non-polar molecules will experience London forces. So this is what I was alluding to about 5 minutes ago. Intermolecular forces determine states of material. When you have strong intermolecular forces, you hopefully have a solid. So let's make a little chart. Our three types of matter are solid, liquid, and gas. There's a constant battle between the intermolecular forces that want the molecules to get closer together and kinetic energy. Kinetic energy wants the molecules to get further apart. What is kinetic energy? Energy of motion, exactly. Yes, energy of motion. It's how much energy molecules have when they're moving around. So toddlers have a lot of kinetic energy. They're always moving. Right now, you have very high intermolecular forces because you are fixed to your chair. You've been told it is rude to walk around the room while a teacher is talking, so you sit in your chair. When the bell rings, you're no longer constrained, and you'll get up and move. You will have more kinetic energy. So let's make a little chart with a solid, comparing intermolecular forces to kinetic energy. Should I put a less than, an equal sign, or a more than there? Well, why don't you just talk with your neighbor? Take 10 seconds to convince your neighbor, for a solid, is intermolecular force larger, smaller, or equal to kinetic energy?
I think it's less because we just compared our cost to a solid and we're seeing
Okay, who says with a show of hands, who says we should put an approximately equal sign here? Who says we should put a smaller sign here? Who says we should put a larger sign here? Yeah, let's put a larger sign there. For a solid, in the battle between intermolecular forces and kinetic energy, the intermolecular forces win. With a gas, it's the kinetic energy that wins. And with a liquid, we'll say it's a draw. Okay? So that's how intermolecular forces determine what state you have. If you have a solid and you want it to turn into a liquid, what do you do? How do you melt it? Heat. You heat it up, right? So what does heat do? Heat increases the kinetic energy. So when you increase the kinetic energy, you can melt something. On the other hand, if you want to turn a liquid into a solid, freeze it. Take the kinetic energy, drop the kinetic energy, and a liquid will become a solid. Okay. The intermolecular force